Okay, so for this program, we did quantum well. I'm Joanna.
I'm Danielle.
I'm Fredy. In this program, we deal with the equation, and throughout the program, we prompt the user to enter values to different variables that will be used to find solutions to the equation. Once we have established the values, we then proceeded to plot the left and right sides of the equation to see where the intercepts, which are also the solutions, occur. Once the program has solved all of the solutions within the established range and position, it will store them in a column vector. Then finally, the user can choose to see a specific math solution. Therefore, the main purpose of this program is to find solutions for the equation and allow for the user to choose to see one of the solutions and continue to do so if they choose.
Okay, so the first command is just simply to close everything to make sure your variables are completely clear and your graphs are all closed. For task 2, we prompted the user to enter an n value which will later be used, and if they don't enter an n value, it'll automatically be set to 1000. In task 3, we then prompt the user to enter an x0 value, and if they don't, then it would also be a 20. For the solutions, it can't be greater than the inputted xo, and if they don't input anything, then it will be a 5. We then use the equation x equals linspace of 0 round x0 divided by pi times pi, comma n. In task 5, we then ask for precision. We made sure that the user does not input a position that's too small or too big, because this will not yield accurate results. If they do not enter anything, we set a position up to 0.18 because this will give the right amount of solutions that we're looking for. Task 6 is where we decided to plot the equation. This y equals 1 divided by tangent x will be the left side, and z will be the right side, as you can see here. It will then plot this equation and make sure that we use the hold on and hold off commands, because if not, it will plot it in two separate graphs. Then in task 7, this is where the user gets to see what the solutions are. So all of this is just pretty much what shows what the solutions will be, and your all command will be all of the solutions possible. The user will then be prompted to see if they want to see one single solution, and if they don't, they have that option by simply pressing 0, and the program will automatically end. If they press 1 though, they will be asked to enter what solution they want to see, and that would be your m value. Finally, in task 8, the user will be prompted to see if they want to run more solutions. If they don't want to, they can always press 0 and the program will automatically end. However, if they want to continue seeing more solutions with different inputs or the same inputs, they simply type in 1 and the program will begin from task 3 over and run through the entire process. Okay, now that you know the code, this is the way that it runs. Okay, here it's asking to enter a value of n that you wish to use. You can either choose to enter a value of n, or you can just simply put enter and it'll just assign the values that were assigned in the code. So for this time, we're just going to press enter. Now it's asking for the value of x0, simply press enter again. For the number of solutions, we could do the same thing. Warning. Here we get a warning sign saying that if we have a small number of sampling points and high precision, then it will not give us very accurate results. Therefore, we need to make sure we are careful when entering a max error. So in this case, we'll just press enter to set it to 0.18. Here I plotted the graph, and you can see where the blue and the green intersects. This is where you need to find, these are the solutions that will be later given. Our range is set from 0 to 4 pi, that's why it cuts off at this point. But that's okay, because we only want the solutions within this range. Now going back to MATLAB. It asked if we want to see a specific solution, so we put yes. Now it's asking us for which solution. You can type in any m solution you want to see, but in this case we'll just use 7. Now, our 7th solution is 9.9800. It's asking us if we want to continue finding solutions. In this option, you can continue to use it or just quit the program. In this case, we'll just quit the program. If you want to double check to see if that's the right m solution, simply type in all, and it'll give you all of the solutions. If we count over to the 7th, it's 9.98, just like it had given before, therefore showing that our results are correct.
This is the heat diffusion part of our project. And this program demonstrates the evolution of heat diffusion over a specified time, which is t, by using the relationship of the position equation and the solution of a point source heat equation in a specified position. The first part of our code, clear all, clears all the previous functions as assigned variables. Close all closes all the open figure windows. And COC clears the command window. As for task 2, we will attach a PDF file to the final project. And as for task 3, the user is prompted to enter values for x naught, y naught, and z naught. In all three, the user must enter a value that's greater than negative 400, but less than 400.
For task 4, the user is prompted to enter a value for t. We've set up our x, y, and z to be lin-space functions going from negative 400 to positive 400 in intervals of s. For this program, we made s equal 81. We have our constant k, and this program is used as c, and we've set it to equal 25,000. To set up the plot for u, we've also created 4 for loops, putting our t in terms of I, j, k, and l, x, y, and z in terms of j, k, and l. And we've set up our u, so therefore we've set up our u function to equal the heat diffusion equation given in the prompt, except for in terms of x in terms of j, y in terms of k, l in terms of z, I in terms of t, and so on. We've used the mesh function to plot this parametric mesh of 4 dimensions. And in task 6, we use the figure function again to open a new figure for this part of our program, and we use the contour function to plot u in 21 slices, creating the values of u as heights above a plane. We use a C label function to add height labels to our given contour plot of C, and we use the axis type function to plot an axis of the extent of the bounds of our contour plot. For task 7, we create an animation, or a movie, so to speak, of our u and how it changes over time. We set up a for loop by putting t equal from 1 to the inputted t, using another figure function so it pops up in a new window, using again the same mesh function to plot u, changing our axes to a set of bounds that the image plots so that it remains constant even as the interval changes over time. And we use the pause function to equal 0.5 seconds so that this command keeps as it changes over time, creating a movie. The end function then ends the loop. If we run the code, we are prompted to enter x naught, can enter any value, y naught, z naught, and enter a value for time. I'll put in 5 seconds. As you can see, the figure 3 has the animation, which is our task 7. If we go back a bit, back in the code, we have our figure 2, which is the contour plot with the points labeled in the contour function. And if we go back to our figure 1, we have our original function u plot in terms of x, y, z, and t. Thank you.